To calculate the cooling load required for lighting, we have to make the following assumptions. First, we assume steady state conditions. By that, we mean that if the cooling load required for lighting at 3 p.m. yesterday was 500 watts, then the cooling load required for lighting at 3 p.m. today is 500 watts. Second, we assume that the lighting itself only produces sensible heat gain. No latent heat gain is produced. Third, we assume that the sensible heat gain is split into radiant and convective portions. Fourth, we assume that the convective part of heat gain immediately becomes cooling load. Finally, we assume that the radiant part is first absorbed by the finishes and masses of interior room surfaces, and it becomes cooling load after it has been transferred by convection from those surfaces to the room air. To perform the actual calculation of the cooling load required for lighting, we have to first calculate the 24-hour heat gain profile for lighting. Then we split the heat gains into radiant and convective portions. Remember that the convective portion immediately becomes cooling load. Afterwards, we apply the appropriate radiant times series to the radiant portion. Then we sum the convective and radiant cooling load portions to determine the cooling load for lighting at the designated time. The sensible heat gain from electric lighting can be calculated using two procedures. One procedure is to use the general formula, which is Qs is equal to W times FUL times FSA. Qs is the sensible heat gain in watts. W is the total light wattage in watts. FUL is the lighting use factor, and FSA is the special allowance factor. The second procedure is to use what we call the space-by-space method. The space-by-space method estimates the lighting heat gain on a per square meter basis, and it is suitable when final lighting plans are not available. In this example, we are going to calculate the sensible heat gain by lighting using the general formula. The problem says, calculate the sensible heat gain by lighting at 3 p.m. due to fluorescent lights, which are non-insulating pendant luminaire, in an enclosed office space of a building of average commercial construction with carpet and 50% glass. The total area of the office space is 12.95 square meter, and the lights are 100% on from 7 a.m. to 7 p.m., then off the remainder of the time. We were given the lighting specification as 1.5 lamp pendant fluorescent 2440 mm type. We were told that the fixture has 532 watts T8 lamps plus electronic ballast, and the special allowance factor is 0.85 per manufacturer's data. We were also told that the lights are 100% on from 7 a.m. to 7 p.m., then off the remainder of the time. That means that at 3 p.m. the lights are still on. So, using the general formula, we can say that the lighting sensible heat gain at 3 p.m. is equal to W times FUL times FSA. Remember, W is the wattage, FUL is the use factor, and FSA is the special allowance factor. So, W is equal to 5 times 32, which is equal to 160 watts. FUL is the wattage in use divided by the lighting installed wattage, and that is 100% at 3 p.m. FSA is equal to 0.85 per manufacturer's data. Therefore, the lighting sensible heat gain at 3 p.m. is equal to W times FUL times FSA, which is equal to 160 times 100% times 0.85, and that will give us 136 watts. Now we are going to calculate the sensible heat gain by lighting using the space-by-space method. It is the same example as before, just that this time we are using a different method. Remember, we were told that the lights are 100% on from 7 a.m. to 7 p.m., then off the remainder of the time. That means that at 3 p.m., the lights are still on. For the space-by-space method, we will use this table, which contains the lighting power densities of common office space types. We were told that the office space is enclosed, so a lighting power density of 10.5 watts per square meter is appropriate. We were also told that the office area is 12.95 square meter. Therefore, using the space-by-space method, the lighting sensible heat gain at 3 p.m. is equal to the lighting power density times the area, which is equal to 10.5 times 12.95, and that will give us approximately 136 watts. The result would have been different if we used a different area and or chose a different office space type. The convective portion of lighting heat gain is calculated by multiplying the sensible heat gain from lighting by the fraction of lighting heat gain that is convective. Remember that the convective portion immediately becomes cooling load. The radiant heat gain from lighting is calculated by multiplying the sensible heat gain from lighting by the fraction of lighting heat gain that is radiant. To calculate the radiant cooling load for lighting, we will apply the radiant time factors and use the following formula, which is the radiant cooling load for the current hour is equal to the 0th radiant time factor multiplied by the radiant heat gain for the current hour plus the first radiant time factor multiplied by the radiant heat gain an hour ago plus the second radiant time factor multiplied by the radiant heat gain 2 hours ago plus the third radiant time factor multiplied by the radiant heat gain 3 hours ago, and so on until we get to the 23rd radiant time factor multiplied by the radiant heat gain 23 hours ago. Now let's calculate the cooling load for lighting using the radiant time series method. We are going to use the same example as before, just that this time we are calculating the cooling load. So these are the tables that we are going to use, table 3 and table 4. Table 3 basically is the lighting heat gain parameter for typical operating conditions, and you can see that there are different luminaire categories for recessed fluorescent luminaire without lens, for recessed fluorescent luminaire with lens, for downlight compact fluorescent luminaire, for downlight incandescent luminaire, and for non-in-ceiling fluorescent luminaire. That's the one that is applicable to this example. Okay, and you can see that the space fraction is 1, meaning that the entire sensible heat gain goes into the conditioned space. That's the implication. You can also see that the radiative fraction is between 0.5 and 0.57. Right, but we're going to use 0.57 because if you check the notes, you'll see that they said use higher value for radiative fraction for pendant luminaire. We're told that the lighting type is of pendant luminaire, so that's why we're going to use 0.57. And for table 4, table 4 is the non-solar RTS for medium construction. We're told that the building is of average commercial construction, that's medium. We're also told that it's with carpet and 50% glass. Okay, so that's why we are using these values. So these are our radiant time factors. So this is the 0th radiant time factor, this is the first radiant time factor, this is the second radiant time factor, this is the third radiant time factor, and so on until we get to the last one here, the 23rd radiant time factor. If you add all of them, you should get 100. I'm going to show you where I got these tables. We have already calculated the lighting sensible heat gain at 3 p.m., which is 136 watts, using the general formula. We were told that the building was of average commercial construction with carpet and 50% glass. We also know that the lighting type is non-in-ceiling fluorescent pendant luminaire. Using the table below, we can see that the space fraction is 1.0 or 100% if you like. The radiant fraction is 0.57 or 57% if you like. and the convective fraction is 0.43 or 43% if you like. So at 3 p.m., the convective portion is 136 times 43%, which is 136 times 0.43, and that will give us 58.48 watts. For the radiant fraction, we will apply the radiant time factors. So at 3 p.m., this will be equal to 0.57 brackets 0.49 times 136 plus 0.17 times 136 plus 0.09 times 136 plus 0.05 times 136, and so on until we get to the 23rd radiant time factor multiplied by the radiant heat gain 23 hours ago, which is 0 times 136, and that will give us 0.57 times 121.04, which will give us 68.9928 watts, or 68.99 watts approximately. Therefore, the total cooling load required for lighting at 3 p.m. is equal to the convective cooling load plus the radiant cooling load, and that is 58.48 plus 68.99, which is equal to 127.47 watts. So I said I was going to show you where I got those tables. That's table 2, table 3, and table 4. I got them from 2013 ASHRAE Handbook Fundamentals. Let me show you where I got table 2. So I got that from page 454. And here you can see lighting power densities using space by space method. Alright, if we scroll down, you see that for offices, for enclosed offices, the lighting power density is 10.5 watts per square meter, and for an open plan it is 8.1 watts per square meter. Alright, if we go up, you can see it here. The lighting power density is in watts per square meter. So let me show you where I got table 3. I got that from page 455, and you can see lighting heat gain parameters for typical operating conditions. And under luminaire category, you can see non-insulating fluorescent luminaire, and for this the space fraction is 1 and the radiative fraction is between 0.5 and 0.57. And you can see under the notes, you can see here at the bottom, use higher value for radiative fraction for pendant luminaire. That's why we're using 0.57. And for table 4, I got that from page 477. If we go down, you can see representative non-solar RTS values for light to heavy construction, and you can see under medium with carpets and 50% glass, we have the radiant time factors that I showed you earlier. So this is the summary of our cooling load calculation for lighting. That's for a 24-hour period. You can see the R, you can see the usage profile, you can see the heat gain, both convective and radiant. For convective it is 43%, and for radiant it is 57%. You can also see the non-solar radiant time factors here. You can see the radiant cooling load. You can also see the total sensible cooling load and the room sensible cooling load. The total sensible cooling load is the same as the room sensible cooling load if you compare the values. All right. Below this is a breakdown of the radiant cooling load calculation. Right, you can see for 1 a.m. it is 9.3024 watts. For 2 a.m. it is 9.3024 watts. Also for 3 a.m. it is 8.5272 watts. And you can also see the value for 4 a.m. and every other hour until we get to 12 a.m. That's 10.0776 watts. Let me show you the one for 3 p.m. So for 3 p.m. it is 68.9928 watts, and that's what we got in our calculation. All right. For the graph, I used a Python library to plot this graph. That's matplotlib, but you can use any other application of your choice. You can use Excel if you like to plot the graph. Let me zoom in so that you can see it properly. Right, so this is what the graph looks like. And like I said, you can use any application of your choice to plot it, but I used a Python library called matplotlib to plot the graph. Right, so that's basically how it works.